Hello, my name is Harrie Weinans. I work at the Department of Orthopedics of the University Medical Center in Utrecht in the Netherlands, and I'm going to entertain you for a few minutes with work that we do on osteoarthritis, where we use novel imaging in small animals, specifically mouse and rats, where we use a lot of the MI Labs equipment. Okay, if we talk about osteoarthritis, we basically talk about cartilage. And most surgeons, orthopedic surgeons that I collaborate with, they see osteoarthritis as a disease of mechanical wear and tear. The cartilage basically wears out in time. And sometimes that can go fast. If you have weak cartilage, if you have strong cartilage, that might take long. But anyway, they look at it as a mechanical disease. If you talk, however, to a rheumatologist, he will tell you that osteoarthritis is basically a rheumatological disease, and there is a lot of inflammation involved that has aspects that relate to the immune system. So, and of course, both are to a certain way true. So osteoarthritis, I see it as a disease where mechanics meets immunology. The question really is the chicken or the egg? And I always tell people that ask, okay, what comes first? Is there first wear and tear and then immune cells? Or is there first immune cells and an inflammatory process and then there is wear and tear? And I always tell them, well, it depends on your imaging equipment. Nowadays, companies like MI Labs can make imaging equipment that is so sophisticated and so sensitive that you can see a lot of details about processes, etc. So whatever imaging system you have, if you have something that can show very well immune aspects, you might say, oh, it's the immunology that comes first. If you have equipment that can visualize the wear and tear very well, so for instance, the damage of the cartilage, you might say, oh, there's first damage of the cartilage. So it depends really on the tools that you have, and these tools getting better and better every day. So let's have a quick look. What is cartilage? How does it work? So cartilage is basically a shock absorber. So when you squeeze on cartilage, water is constantly squeezed out, and if you unload the cartilage, the water gets back. So there is a continually squeezing of cartilage, of water in and out the cartilage. And there's a lot of issues that are related to this water metabolism in the cartilage. And one of them is related to the direction of the fibers of the collagen. So on the right, you see a piece of bone, and you nicely see the orientation of the bone trabeculae. And as you can see, they are nicely oriented in the direction of the mechanical loading. And with cartilage, although it's not as obvious, it is more or less the same thing. Cartilage is a load-bearing tissue, and the fibers of the cartilage are sort of made according to a beautiful cave almost, so that they are very optimal in carrying the loading. In particular, when it is a lot of water in there that has a lot of friction with the fibers of the collagen, then altogether it gives it a very strong mechanical structure. Okay, so what do we do to induce osteoarthritis in a small animal? There's many different things that we can do to induce osteoarthritis. And as in humans, osteoarthritis can develop as a consequence of many different reasons. So one way to induce osteoarthritis is to just inject a compound that actually damages the cartilage directly. Things like monoiodoacetate or collagenase. Collagenase is an enzyme that actually digests the collagen fibers in the cartilage. And of course, then you create immediate damage to the cartilage, and that leads to damage and osteoarthritis. But there's also genetically modified mouse that actually can get cartilage very fast. Or you can cut a ligament in the knee of a rat, which is a well-known model. And because of this ligament resection, there is more friction in the joint, and because of that friction, you get you develop fast osteoarthritis. What we also sometimes do is that we place little damaged grooves on the surface of the cartilage, and that also then develops further and further and generates osteoarthritis. Another model that we use is to have rats run for about 5 kilometers a week. Apparently that seems to be enough to create an overloading in the joint, and because of that overloading they also develop osteoarthritis. So there's many different models that we can use, and a specific way of studying this is by the visualization of different aspects that happen in these joints. So what we often do is that we use micro-CT and microspect, and here's an example of the MI Labs equipment that we use for that, and typically we go for around 1, 2, 3 months mostly, and then we study the development of the changes in the tissue of the joint, and we can thereby visualize the bone in the joint, we can visualize the cartilage, but we can also visualize aspects of the immunological systems that occur in these joints. For instance, we can visualize active macrophages, and I come to that in a few minutes. Here's an example of the accuracy that you can get with these imaging equipment. This is a high-level imaging of a mouse knee, and I mean, think about it. The total size here is well, the width of the knee is in the order of 1 millimeter. Yeah, so this should be a quite high resolution to see some details of what is going on in these knees. So the top is basically a bisphosphonate scan. Yeah, so these bisphosphonates are taken up in the bone at every location where there is high turnover of bone tissue, and there is a technetium dye attached to the bisphosphonate, and thereby we can visualize the uptake of bisphosphonates in the mouse bone. And as you can see, the dark dots over here, yeah, that's where the diphosphonates are taken up in these bones. And in the bottom row, you see a high resolution micro-CT of the same joint made at the same time. And if we register the two, that's on the next picture, we get typically these kinds of pictures. So left column is the SPECT scan, the right column, the middle column is the CT, and on the right column you see in blue the CT, and in red you see the SPECT, the bone scan basically. So you see the red dots in the bone scan within the blue bone tissue, and so on row 4, for instance, you can see where there is a high uptake of the bisphosphonates, and that means that there's a high turnover, and this represents the growth plate of this mouse. And in the right panel you can see it even better. Again, the SPECT scan, then in the middle column the micro-CT, and on the right column the registration of the two. And now it's the longitudinal pictures, and you can quickly see that the growth plate is actually popping out from the SPECT scan. So with this methodology you can precisely pinpoint where things occur in the bone, for instance. Here you see the results of a micro-CT scan that comes from a mouse knee in which osteoarthritis is induced. Here the osteoarthritis is induced by injecting a compound that actually wears out the collagen fibers. And on the left you see the control joint, on the right you see the osteoarthritic joint. And as you can see, there's a lot of changes in the bone. There is these perforations, there's a very thin bone end plate over here, and there's thickening on the right side. So as you can see, there is high turnover in this bony joint, and that is typically for osteoarthritis development. Here again you see the segmented scan, and we try to find on a histological slide on the bottom part, we try to find the location, the same location of this perforation that you can see over here in the segmented scan on the top, and that's what you see here. And in detail you see that there is a red staining, and that red staining is belonging to osteoclast. So at the location of an osteoclast, we see the red staining, and that's exactly where the osteoclast is actually digging a hole into the subchondral bone plate that perforates through the bone. And then we made some image analysis to actually find out precisely all the locations of these perforations. And on the top row, you see the mouse where osteoarthritis is induced, and on the bottom row, you see the control site. And on the top row, you see that at week 0, there's basically very few of these perforations. And then 2 weeks after we induced osteoarthritis, you see a lot of these perforations in the subchondral bone plate. And actually, that starts off between week 0 and week 2, and then afterwards, it's more or less constant. Whereas at the control site, there's no increase in these perforations. Again, we did histology on the same bones, and we again see the active osteoclast here in red stains. Yeah, and you can see that there's these huge osteoclasts that eat their way through the subchondral bone plate. So imagine, we have injected something in the joint space, so where the joint fluid is and where the cartilage is, and then within 2 weeks from the bone part, there is an active osteoclast eating their way up to the cartilage. So apparently these two areas communicate with each other. So apparently the cartilage puts signals to the bone, and from the bone, cells eat their way to the subchondral bone plate in a sort of rescue mechanism for the cartilage. And of course, this rescue mechanism is something that you don't want for osteoarthritis development, because we see all these bone changes and they even harm the joint even more, and that leads to progression of the osteoarthritic process. In another model, we had rats that we let run for about 1 kilometer a day, and apparently that is sort of an overdrive for these rats. So this is too much running for their joints, and so we train them first for about a week to slowly get used to this 1 kilometer a day running, and then after that we do that for around 6 weeks. And the consequence of that is that they get changes in their cartilage structures, and you can see that over here. So the red staining means that there is proteoglycans in the cartilage, and these proteoglycans, they are very important for the well functioning of the cartilage. So you see it that on the control side, there's nice proteoglycan staining in all the cartilage layers, and in the rat that had run 1 kilometer a day during a period of 6 weeks, we see there is a lot of this proteoglycan staining is gone. Over here, it's complete leakage of proteoglycans, and here in the patella joint with the trochlea, you also see that there is almost complete leakage of the proteoglycans. And also on the bottom right part, you see that the leakage of proteoglycans. And here in an amplification, you see that there's even cells at the bottom part of the cartilage that become hypertrophic, which is also a sign of the slowly developing osteoarthritic process. And again, in these running rats, we see the same phenomenon. Again, at week 0, we almost don't see any perforations, but at week 6 and week 12, we see a lot of these perforations. So again, the subchondral bone plate has changed a lot. So during the process, the proteoglycans are leaking out of the cartilage, and at the same time, osteoclasts are eating their way through the subchondral bone plate to the cartilage. And that's what you see here on the bottom row, these red dots. As I said, there's many different phenotypes of osteoarthritis, and I always say that in humans we see the same thing. There's different phenotypes, yeah. And so in the different models that we use, we also get different processes and different sort of speed how osteoarthritis develops. But what we always see, no matter what we do, there's always the same phenomenon of these subchondral perforations. So as soon as you have a lot of these perforations, there's a lot of interaction between the bone compartment and the cartilage compartment, and it turns out that that always speeds up the process. Another important thing that we look at is this proteoglycan loss. And this proteoglycan loss leads to a lot of loose fragments of proteoglycans, and we hypothesize that these fragments have an effect on the macrophages that become active in the joint space. So if this is a cartoon of the cartilage, and these are the collagen fibers, and then these blue parts with these side chains are the aggrecan or proteoglycan molecules, then during the process of osteoarthritis, we see that these side chains of proteoglycans are leaked out in short fragments. And these short fragments, when they come into the joint space, they have to be removed, and our immune system is an important part of the removal of all these fragments that come out of the cartilage. And so the macrophages consume basically these fragments, and then they take care of the removal. They become smaller. So enzymes are being made to actually cut these fragments in even smaller pieces, and then the body can get rid of it. So what we're interested specifically in is how is the activity of these macrophages. And one way to do that is to use folate. As macrophages that become active, they express folate receptors. So a person that we collaborated with was Phil Lowe from the United States, and he developed this folate imaging, and he did that specifically for cancer cells, as cancer cells also have a lot of folate receptor. So he designed folate with a radioactive tracer. So he coupled this radioactive tracer to folate, and by doing that he could inject this new formula of folate with the tracer, and then you can follow where the folate goes using SPECT imaging. So you can stick the animal into the SPECT scanner, we label the folate with indium, and then we can visualize where the indium goes. That tells us where the folate goes, that tells us where the active macrophages are. And here you go. So on the left, we see a model in which we have fed rats with a high-fat diet. And so we have two groups. One where we feed them only with a high-fat diet, and the other one, we feed them with a high-fat diet, but at the same time, we place small grooves on the femoral condyles of these animals. So, and if we do that, we expect that the grooving on the femoral condyles creates an inflammatory process, but that inflammatory process is in particular active when the rats are, so to say, having a lot of fat, because fat induces inflammatory processes. So if there is a combination of groove on the femoral condyles with a high-fat diet, we expect to see a lot more inflammation in the joint than without the high-fat diet. And that's exactly what you see over here. So here's the sham-operated group with the high-fat diet on the right, and on the left, the standard diet. So basically, you hardly see any activity of macrophages in the joint. And on the right, you see now rats where we have placed grooves. On the left, again, with the standard diet, but if there is a combination of placement of grooves in the joint with a high-fat diet, we see that there is a lot of these macrophages that become activated in the joint. So this is an indication why high-fat diet in combination with small damage creates a lot of inflammation in your joints. And this is exactly what we hypothesize in humans, because people that have overweight, the more overweight you have, the higher chance you have on getting osteoarthritis. And likely that's not only because there's more weight and more loading on the joints, but that's also because there's more inflammation in your joints. So altogether, we now looked at the differences in macrophages. So macrophages can be sort of grossly subdivided in M1 and M2 macrophages. And it turns out, after more detailed study, that in particular the M2 macrophages that are part of the repair process, that they have the folate receptor and not so much the pro-inflammatory macrophages. So apparently this process, these macrophages that you see here, is an attempt of the body to repair rather than creating inflammation itself. Well, I would like to end with this slide. On the left panel, you see all kinds of characteristics of a healthy joint: normal bone, nice intact cartilage. You have some activated macrophages, but not much. You might have some enzymes that take care of all kinds of fragments that leak out. Yeah. And on the right, we have an osteoarthritic joint where we have all these perforations, we have all these enzymes, we have all these activated macrophages that occur here in the joint. And so using these equipments, we can visualize all these different aspects separately and thereby studying how the process of osteoarthritis develops. Okay, I would like to end with mentioning my funding agents. As you can see them here. And I thank you for your attention.